Hey there, we're going to work some impulse and momentum examples together. The first two deal with a single object. So we have a momentum change happening on a single object. Number one says that we have a baseball, its mass is 0.25 kilograms, and it's moving towards home plate with a velocity of 45 meters per second, and then it's hit away from home plate with a velocity of 55 meters per second. So the first thing we need to notice there is it's traveling in different directions. So that means that we're going to end up with a positive and a negative velocity. So if we say that it's a 45 meters per second towards the home plate, when it's hit away, it's going to have a negative 55 meters per second velocity. So important thing there is recognizing we're going to have a sign difference in our velocities. And we're going to assume the bat is in contact with the ball for 6 times 10 to the negative 4 seconds. And then we're going to calculate the average force exerted on the ball. And so for this one, remember an impulse, force times time, is equal to a change in momentum. And since this is a single object, the mass doesn't change on the object. The only thing that's changing is the velocity. So we can rewrite that as m delta v. Okay, so it's a change in velocity times the mass of the ball. And so we could rewrite that. So net force times time, my impulse, is equal to m delta v. I have my change in velocities, and I have my mass and my time. I'm solving for the net force. So I'm going to divide both sides by time. So that average net force is going to equal the m delta v divided by the time. And from here, we can just plug in our numbers. And so the mass of the ball is 0.25 kilograms. The final velocity, because remember change in velocity is final minus initial, we have a negative 55 meters per second minus the initial, which is 45 meters per second. So we're going to end up adding those two numbers together because they're both negative there. And then that's going to be all over our time, which is 6 times 10 to the negative 4. Now, remember on your exponents, all that means that times 10 to the negative 4, that just means we have 6 and we're going to move it 4 to the left. And so down here on the bottom, we'll put 6 times 10 to the negative 4. Now, when you punch that in the calculator, we'll take some time a little later to practice that, but you're going to type that as 6, use your exponent button or the EXP or the EE button, and then negative 4. And so when we plug all this in, we end up with a net force, is 50,000 newtons to the left, right? Because we ended up with that negative answer there. And so there is my answer. Number 2 says that we have a cart with a mass of 2 kilograms. It's initially traveling to the right at 4 meters per second. There's an external force of 80 newtons applied to the cart towards the left. Okay, so that's important. And the time there is 0.2 seconds. And we're asked to calculate the final velocity of cart A. So let's kind of write down what we have. We know the mass is equal to 2 kilograms. We know that it's traveling to the right, so we'll call that positive. So your velocity is equal to 4 meters per second. And there's a force that's applied to the left. So that force there, we're going to call that negative. Okay, we want to use negative in our calculation. So negative 80 newtons. And the time is 0.2 seconds. And we're trying to solve for that final velocity, right? We want to know what the final velocity is equal to. So in order to calculate the final velocity, we're going to need to find our final momentum. And we have enough information to solve for the initial momentum because we have the initial velocity and we have the mass of the object. But we don't know the final velocity. That's what we're solving for, and we need the final momentum. So to solve this, we're going to have to first find our change in momentum. And they gave us a force and the time on this, so we can go in and we can solve for our change in momentum using our impulse momentum equation. So we know that a net force times time, your impulse, is equal to change in momentum. And the net force here, we had negative 80 newtons. And the time we had was 0.2 seconds. And that's going to be equal to my change in momentum, that delta P. And I get negative 16 newtons times seconds. Now that I know my change in momentum, we can go in and we can solve for that final momentum. Now, first, let's find the initial momentum. And so the initial momentum, we had 2 kilograms times the initial velocity, which was 4 meters per second. So we had 8 kilograms times meters per second. Now, remember, newtons times seconds and kilograms times meters per second, that's the same thing, right? It's the same unit. So let's go in and solve for this final momentum. So we have delta P is equal to the final momentum minus the initial momentum. We have the change and we have the initial. We're going to solve for the final momentum. So I'm going to add the initial momentum over. So your final momentum is just going to equal the change in momentum plus the initial momentum. And we found our change in momentum. It was equal to negative 16 kilograms times meters per second, plus the initial momentum, which was 8 kilograms times meters per second. So your final momentum is equal to negative 8 kilograms times meters per second. Now that we know the final momentum, we can go in and solve for that final velocity. So the final momentum is equal to the mass times the final velocity. And so I'm going to divide both sides by the mass. So your final velocity is going to equal your final momentum divided by the mass. So we have negative 8 kilograms times meters per second divided by the mass of the object, which was 2 kilograms. My kilograms are going to end up canceling there. And I'm left with negative 4 meters per second. Or I could say 4 meters per second to the left. Okay, so there's a couple examples when we have one object and we're trying to use our impulse momentum equation or solve for the final velocity of the object. Now we're going to look at momentum change from a graph and then the momentum change of a system of objects. So number 3 gives me, it says there's cart A, its mass is 2 kilograms, it's traveling to the right 4 meters per second. There's an external force that is a variable external force. That means it changes, it's not a constant force. It's applied to the cart over 4 seconds. And then they give us a graph here, the force time graph, and we're asked to calculate the velocity of the cart after 4 seconds. Okay, so remember, from a force time graph, we can find the area underneath the curve, and then we can solve for the impulse, which is the change in momentum. So we know that impulse is equal to change in momentum. So on our graph here, when we find the area under the curve, we're finding our impulse or my change in momentum. So your delta P here is just equal to the area under the curve. So we're going to break this up into some shapes that we're familiar with. We have a triangle right here. We can make a triangle right here. And then we have this square right here. So your change in momentum, delta P, is equal to the sum of all those areas. So the first triangle, we have the area is 1/2. The base, we have 2 seconds. Times the height, which is negative 20 newtons. Plus we have the area of the next triangle, which is 1/2 times the base, which is now 1 second, times the height, which is 10 newtons, plus the area of that last square, which is length times width. So we got 1 second times 10 newtons. And then when we add all these up, you should end up with a change in momentum of -5 kilograms times meters per second, or newtons times second. Right, same thing. And the problem gave me enough information to solve for the initial momentum of this cart. So my initial momentum is equal to the mass of the cart times the initial velocity. Oops. There we go. So the mass of the cart is 2 kilograms. And then the initial velocity was 4 meters per second to the right, so that's positive. So we got 8 kilograms times meters per second. So we have the initial momentum and then change in momentum. From there, we can solve for our final momentum. So the final momentum is equal to the change in momentum plus the initial momentum, kind of like that last example. So the change was -5 plus the initial was 8. So your final momentum of the cart is going to equal 3 kilograms times meters per second. Now that we know that final momentum, we can go in and solve for your final velocity. So your final velocity is equal to the final momentum divided by the mass of the object. So that gives me 3 kilograms times meters per second divided by 2 kilograms. And so your final velocity is just equal to 1.5 meters per second. So when we have a force time graph here, we can go in and find the area underneath the curve, and that will tell me my change in momentum or my impulse. And the last example here, it's a system that has 2 objects. Now we're looking at a system of objects. And it says first that we have a 4 kilogram object moving at 2 meters per second to the left. And so this one, we're going to have a lot of different numbers. So we're just going to kind of write this out as we're going through it. So I'll call that M1 is equal to 4 kilograms. And the initial velocity, V1, since it's to the left, we'll call that negative. So we got -2 meters per second. And then we have a 12 kilogram object, so I'll call that M2. That's the mass of the second one. And it's equal to 12 kilograms. And it's moving 4 meters per second also to the left, so it's negative. So your V2 is equal to -4 meters per second. After 2 seconds, so we know we have our time is equal to 2 seconds, the 4 kilogram object is now moving 4 meters per second to the right. So let's go ahead and again, let's write that down. So afterwards, we got the mass of object 1, it's still 4 kilograms, but now the velocity of object 1 is equal to 4 meters per second. And it says the 12 kilogram object is at rest. So the mass of your second object is still 12 kilograms, but now the velocity is 0, it's at rest. And we're trying to find that net force on the system. And so to kind of start this out, we have enough information, we can solve for the initial momentum on this system. And so the initial momentum is equal to the momentum of cart 1 plus the momentum of cart 2. So 4 kilograms times -2 meters per second plus 12 kilograms times -4 meters per second. And when we plug this all in, your initial momentum of the system is equal to 56 kilograms times meters per second, but it's negative, right? We have a negative because both of those negative velocities. So be careful with your signs there. We also have enough information we can solve for the final momentum of the system. So your final momentum of the system is going to equal the 4 kilograms times 4 meters per second, plus we had 12 kilograms times 0. So the final momentum of your system is equal to 16 kilograms times meters per second. Now from here, we have the initial and final momentum, so we can solve for the change in momentum. So your change in momentum is just the final momentum of the system minus the initial momentum. So the final momentum was 16 kilograms times meters per second, and our initial one was negative 56 kilograms times meters per second. So it's minus a negative, so we're going to end up adding those numbers together. So your change in momentum of this system is 72 kilograms times meters per second. Now we can go in and finally solve for that force, that net force on the system that they wanted, using our impulse momentum equation. So the net force times time, that's your impulse, is equal to your change in momentum. And we know the time, and we know the change in momentum, so we can go in and solve for the force. We'll divide time by both sides. So your net force is equal to the change in momentum divided by my time. Change in momentum was 72 kilograms times meters per second. And then the time was 2 seconds. So the net force on this system is going to equal 36 newtons, and then that would be to the right because it's positive. So there's some examples of working with a momentum change of a system of objects using our graph here on a force time graph, and then also when we have a single object.